Alright, 40 is all about the calculus of work. So we're going to be dealing with a force that isn't constant. It depends on position, and so we're going to be dealing with all this stuff. Area under the graph. Actually, and we're going to do both integral and derivative, interestingly enough. So that's going to be cool. Let's check it out. 40. So if you read 40 real quick, you get a block that is having a force applied to it, and the force is 2.5 minus x squared newtons. And yeah, it acts in the I direction according to the book, but really what's important is that everything's just moving in one dimension for this. 2 dimensions would be a little crazy. So I'm just going to not even put the I here and go from there. And basically this problem is talking about going from a position of 0 to a position of 2. 0 meters to 2 meters. And that's it. So, well, we know that work is the integral of f dx. Let me write it. There we go. F dx x, right? And part A, by the way, we're looking for the kinetic energy when it's at 2 meters. So not only does work equal the integral of f dx, but there's actually another concept we're dealing with in this problem. This one, work is a change in kinetic energy. So dun da da and dun da da. Alright. Nope. And which, by the way, is KE final minus KE initial, which, by the way, the problem states that the block starts at rest. So I always make those too big. There we go. Ah, I didn't even hit undo that time. Did you see that? This all disappeared. I hit erase, and I erased something. I guess erasing is technically undoing, right? This program, I'm gonna do something to it. So let's integrate. We're looking for this, which is gonna equal the integral of our force with respect to x. So let's do that. Work is the integral from 0 to 2 meters of 2.5 minus x squared with respect to x, and that equals the integral of 2.5 is 2.5x. The integral of x squared is x cubed over 3, and we're evaluating this from 0 to 2. Maybe I'll just be nice for now and do meters there. And we know we got to evaluate this at 2. That's the final minus the initial. So this is 2.5 times 2 minus 2 cubed over 3. And that's evaluated at 2. Now we could evaluate it at 0. So minus 2.5 minus all of this. 0, 0, minus 0 cubed over 3. Of course, none of this equals anything, so anyway, so this equals 2.3 3 joules. Yeah. So that's the answer for part A. The kinetic energy at 2 meters is 2.33 joules. We just evaluated that. By the way, what does this look like? What does this force look like? So here's a graph of the force with respect to position. So 2.5 minus x squared is an upside down parabola shifted up by 2.5. So that's just like that, right? This is 2.5 here. And by the way, 2, here's 1-ish. And 2 would be here. Okay. So when we want to find the work, we're finding the area under this graph. So this 2.33 is literally the area of like this piece, like in here, and then here's 2, and then the area of this little piece, like in here, is negative. So this is probably, well, this is definitely higher than 2.33. I don't know exactly what. This is negative and tiny, so this minus this equals 2.33. So graphically, that's what we're doing with all of this. Integral of f dx is the area under a fx curve. And when we integrate that, oh god, stuff's gonna disappear. Get ready. What disappears? Oh, nothing? I don't think anything disappeared. Cool. Anyway, yeah. So let's graph the integral. Let's graph 2.5x minus x cubed over 3. That looks like it's a cubic, so it looks like oh, that's horrible. Ugh. This should be symmetric. Like this hump shouldn't be bigger and wider than this. Sorry. So anyway, 1 is about here. 2 is about here if you graph this. And what is this a graph of? Well, this is x. This is work, but really it's also the kinetic energy final. Work is the kinetic energy final. So we could put W for work, but let's just, since part B is asking for the maximum kinetic energy, let's call this kinetic energy final. And you can see the kinetic energy is 0 at a position of 0 because we're at rest, right? So 1/2 mv squared is 0. But then the kinetic energy increases up to about here. But think about what's happening. We're moving from 0 to 2, so we're moving in the positive direction, right? And for most of that, we have a positive force acting on us. So positive force in the positive direction means we're going to speed up all the way till here. So that's what we're seeing. Kinetic energy is increasing because we're speeding up. Now the force is 0, so suddenly we're not speeding up anymore just for that brief moment. Then the force becomes negative. So we're still moving in the positive direction, but our force is in the opposite direction. That's going to slow us down, right? And so that's why the kinetic energy drops here. Long story short, part B is asking for the maximum kinetic energy. And that is right here, which coincidentally enough is where the force equals 0, because that's where the force changes from moving in the positive direction to moving in the negative direction. And so, calculus-wise, this is really just the derivative of dke final dx, or more specifically, the derivative of work, because this is also a work graph, because work equals kinetic energy final. So this is a little more of an appropriate way to write it. And that's going to happen when the derivative is 0, or when the force in this case is 0. So what is the derivative of work? Well, it's just our force. So 2.5 minus x squared. So solve this for x. X is going to equal square root of 2.5, which is 1.58 meters, which you can see happens between 1 and 2, just about halfway. Same, that's how I drew it here. So this is the position where the kinetic energy is the max. And so take that position, stick it into our kinetic energy function up here, and that will give us our maximum kinetic energy. So 2.5 times 1.58, that's our x here. minus 1.58 cubed over 3. I just did that right here. Now we're evaluating it at 1.58, so we know that it's a little less than 2. So, but we should still get a higher value than this. And we do. We get 2.64 joules. This is the highest kinetic energy we get right here before it starts decreasing again. This is a cool problem. A lot of good calculus in here. And I hope you took the time while watching this video to try to understand how the graphs relate to these equations here. Very important to understand this stuff. So if you didn't, maybe rewatch this or pause it while I'm talking about the graphs and think about it yourself. Good stuff here, good stuff. If you understand this, you're well on your way to doing well on any calculus stuff that's on the test. See ya.